Welcome back everyone, and now we're going to continue with section 14.7. In the last video we talked about local maxes, local mins. In this video we're going to see how we can find the absolute maximum and minimum values of a function of two variables. In Calc 1 we needed a function to be continuous on a closed interval to guarantee that we could find an absolute max and min. So what do we need for a function of two variables? Instead of a closed interval, we're going to need a closed and bounded set. And so let's define what that is. In R2, a set's closed and bounded if it contains all of its boundary points and it doesn't go to infinity. So if we look at the three examples we have here, this rectangle with its interior is closed because I'm including the boundary of the rectangle itself, and it's bounded, right? It's not going to infinity in any direction. This disk without the circle is open because it doesn't contain the circle itself, but it's still bounded. It's not going to infinity. If I included the circle, if I made this a solid circle, then it would be closed and bounded. This, as it is not a set we're going to talk about, but if I included the circle, it would be. So this is what the kind of set we're going to be talking about. This set, what does this say? It says all points x and y, such that x lies between 1 and 2, the closed interval, so 1 and 2 are included, and y is strictly greater than 3, so y can equal 3, and y can go to infinity. This is not a closed set because it doesn't include the case where y equals 3. That set of that line segment of the boundary is not included, and it's not bounded because y can go to infinity. So this is neither closed nor bounded. This is not the kind of set we're going to talk about. Just for a quick side note, something that's interesting, this set's not closed. It's also not open. So closed and open, it does not form a dichotomy of sets. A set can be neither closed nor open, and actually a set can be both closed and open. These are technicalities we don't need to worry about for calculus, but if you're interested in these things, you can take a class called topology. You'll learn all about closed and open sets, and lots of weird things can happen. But anyway, back to what we need. We need closed and bounded sets, so something like this. Now, we have this extreme value theorem, and sorry, I think I spilled some water on my notes. For functions of two variables, you need a function to be continuous on a closed bounded set, so something like this. And let's call that set D. We're guaranteed that f attains an absolute max and an absolute min somewhere in D. So we need f to be continuous, and we need the set to be closed and bounded. Now here I've written at some points x1, y1, that's where it attains its maximum. x2, y2, that's where it attains its minimum. It could be multiple points. We're guaranteed to have at least one each of these, where it's a maximum and a minimum. But you could have multiple points that give you a maximum or multiple points that give you a minimum. Okay, now what we're really concerned with is how do we find these absolute extrema? The first step is to find all local extrema, so what we did in the last video. Find all the critical points of your function in this set and find the values of your function at these points. So we're not going to classify them like we did in the last video. We're not going to use the second derivative test. We're just going to find the values and then compare everything at the end. The second step, which is going to be new for this video, is to find all extreme points, all extreme values on the boundary. So if you remember from Calc 1, if you wanted to find absolute extrema, you checked critical points inside the interval, and then you checked the endpoints of the interval. So this step is kind of like checking the endpoints of the interval, except now we don't have endpoints, we have a boundary on a set. And so we have to check the extreme values of the function on that boundary. We can't check every point. There are infinitely many points on the boundary. And as you'll see, this can get quite involved when we start doing an example. And it's where we're going to spend the majority of our time in the example is on this step. Once you've found all of your local extrema on the inside, you've found all extrema on the boundary, you just compare all of the values you found. The largest value is your absolute maximum, the smallest value is your absolute minimum. Okay, so with that being said, let's go to an example. Find the absolute maximum and minimum values of this function x squared minus 2xy plus 2y on the rectangle D, the interval 0, 3 crossed with 0, 2. So first, how do we read this? These are my x values. X goes from 0 to 3. Y goes from 0 to 2. If I put those two intervals together, then what I get is this closed and bounded region in the plane. So x is going from 0 to 3, y is going from 0 to 2. I put those together. There's my region D. This is closed and bounded. F is a polynomial, so it's continuous on this region. I'm guaranteed a maximum and a minimum on this set. So now let's go through the steps. First, I want to find all the critical points. So to find critical points, we do what we did in the last video. We find the partial derivatives with respect to x and y, and find all values that either where they don't exist or that make both of the partial derivatives equal to 0. So if I take the partial derivative with respect to x, I'm going to get 2x minus 2y, which I have here. Partial derivative with respect to y, I'm going to get negative 2x plus 2, which I have here. These partial derivatives are continuous on our rectangle, so we don't have to worry about any points that make these undefined. All I have to worry about are points that make both of these 0. So I set them equal to 0 and I solve. Here I get the line x equals y. And here I just get x equals 1. So there's only one critical point inside this rectangle, and it's the point 1, 1. Why? Because 1 is the only value that makes this partial derivative equal to 0. And I want them both equal to 0, so if x equals 1, this equation tells me y has to also equal 1. Now from this point, I could use the second derivative test, calculate the discriminant, and figure out what kind of critical point this is. But I'm going to skip that and just find the function value and say, okay, at the end, I'm just going to compare a bunch of function values. So let's just see what the value of the function is there. And the value of the function at 1, 1 is 1. I just plug 1, 1 into this function. I get 1 as my answer. So that's the first step. That's what we've done before. And the second step is finding all of the values on the boundary. This is going to be a bit more difficult. So we need to figure out a way to describe the boundary so that we can find extreme values. So what do I mean by this? It's kind of like parameterizing the boundary, but it's a little bit easier. So what I'm going to do is, let's look at this rectangle. It's made up of 4 line segments, right? So I have a line segment going from 0, 0 to 3, 0, a line segment going from 3, 0 to 3, 2, a line segment going from 3, 2 to 0, 2, and a line segment going from 0, 2 to 0, 0. And here, I don't care about orientation. We're not doing line integrals or anything like that. I just care about these 4 line segments individually. I'm just going to call them 1, 2, 3, 4. And I need to know what the endpoints of each line segment are. And I want to find some way of describing the function on each of these line segments. Before I can describe the function on the line segment, let's look at some information that I have about each line segment itself. So the first line segment, going from 0, 0 to 3, 0, that's all of the points where y is equal to 0, y is not changing, and x is between 0 and 3. So that's how I can describe this line segment. The second line segment, x is fixed, and y changes. So I can describe the second line segment as all points where x is fixed at 3, y goes from 0 to 2. For the third line segment, it's going to be similar to the first one, except now y is fixed at 2, x goes from 0 to 3. And the fourth line segment is going to be similar to the second one. X is fixed at 0, and y goes from 0 to 2. So that's how I can describe these 4 line segments. Now I need to look at the function on each of these 4 line segments and find the extreme values. So let's just start with the function on the first line segment. If I can describe the first line segment with y fixed at 0 and x going from 0 to 3, then when I look at my function, which was x squared minus 2xy plus 2y, if y is exactly 0, I plug in 0 for y. And I keep x a variable, but x is only going to go from 0 to 3. So when I plug 0 in for y, the function on this line segment is x squared, and x goes from 0 to 3. So now I go back. This is now a Calc 1 problem of finding extrema. So how do I do that? I find the critical points of this function, and I test the endpoints of this function. But now it's a Calc 1 problem. So basically what I'm going to end up doing is 4 Calc 1 problems to find the extrema on the boundary. So what do I mean by finding critical points? I mean, I'm going to redefine this as a function of one variable. To find the critical points, I take the derivative. Now it's just an ordinary derivative. It's a function of one variable. Set that derivative equal to 0. That gives me the critical points on the boundary, or this piece of the boundary, rather. So g prime is equal to 2x. I set 2x equal to 0. The only critical point is x equal to 0. But this was already one of my endpoints. So I need to test 0 and 3. I plug those into my function. F at 0, 0 is 0. I can just plug in 0 here. F of 3, 0 is 9. I can just plug in 3 here. So now I have 2 more function values, and these are at the corners of my rectangle, 2 of the corners. Right? There were no critical points on the inside here, so I just needed to test these 2 endpoints. Now I'm going to go to the second piece of the boundary, where x is fixed at 3. So I take my function, and ignore this arrow for a second. I'll explain what that means, or what I'm trying to point out there. X is fixed at 3. Y is allowed to go from 0 to 2. So I just plug in 3 for x and see what I get from my function. So it's 9 minus 6y plus 2y. That's 9 minus 4y. So I have a line here. So the function, scroll this back up, the function on this piece of the boundary is just a line. Now, if I take the derivative, I'm going to do the same thing I did before, try to find critical points. If I take the derivative, this is just negative 4. That's never going to be equal to 0. So I have no critical points inside this interval. I only need to check the endpoints. That's going to be true whenever you have a line. The derivative of a line is never going to be 0 unless the slope is 0, right? So I don't have any critical points inside between 0 and 2, so I just check the endpoints at 0 and 2. And now if I plug in 0 for y, I've already done that. That was the same thing that I found up here, and that's what that arrow means. So really, the only new information I get is when I plug in 2 for y, because basically what I'm doing, I have no critical points in here. I just need to check the 2 endpoints, but I've already checked this endpoint. This is the endpoint of the previous segment. So now I just need to check this endpoint. So when I plug in 2, I get f of 3, 2 is equal to 1. I can just plug in 2 here. Now moving on to the third line segment, y is fixed at 2, x goes from 0 to 3. So now I have this function. I plug in 2 for y, let x be a variable from 0 to 3. The function on the third line segment of the boundary is x squared minus 4x plus 2. This is another parabola. I look for critical points of this function. So call this g. G prime is 2x minus 4. I set this equal to 0 and I solve it. And I get that I have a critical point at x equals 2, which is within this interval. So I have a critical point on the boundary. So that means I need to check the function value when x equals 2, and I need to check the function value at both of these endpoints. So at 2, 2, right, because y is always fixed at 2 on this piece of the boundary, I get the function is 0. At 0, 2, I get the function is 4. And when I plug in 3 at 3, 2, I've already got that information. I had that before, but it's still there. I could do the same thing here, and I get the function at 3, 2 is 1. And now on the fourth piece of the boundary, the last line segment I have to check, x is equal to 0, y goes from 0 to 2. So I plug in 0 for x. I get that this function is 2y. So this derivative is 2. That's never going to be equal to 0. There are no critical points. I only need to check the endpoints. But what do I get when I plug in the endpoints? F of 0, 0, which I've already checked, and f of 0, 2, which I've already checked. So really from this piece of the boundary, I get no new information. Those two values already knew. It's still important to check though, because if this had been a parabola or some other complicated function, I might have had critical points in between the corners that needed to be checked as well. So now I've finally checked all the points on the boundary that I need to check, and now I'm going to summarize what I found and pick out the absolute minimums and maximums. So there were 6 points. This was a critical point inside the domain that I found. I had the four corners, 0, 0, 3, 0, 3, 2, and 0, 2. And then there was another point on the boundary that ended up being a critical point for one of the functions on the boundary. The function just restricted to that piece of the boundary that we had to check. And if I look, out of all the function values, the largest value was 9. So 9 is our absolute maximum. It occurred at 3, 0. And 0 is the smallest value, so our absolute minimum is 0, and that actually occurred in two places. It occurred at 0, 0, and it occurred at 2, 2. So there are 2 points where our function attained its absolute minimum. Okay, so yeah, these problems are a little bit more involved, and really it's checking the boundary. And checking the boundary turns into a Calc 1 problem. In this case, it turned into 4 Calc 1 problems, because we had to check each line segment that made up the boundary. Before we move on, let's take a look at what this function looks like. And this function, which was x squared minus 2xy plus 2y, just on that rectangle, looks like this. And so if we look at this, what immediately pops out, at least what pops out to me, is that the maximum is definitely 9, and it's occurring at one of these corners. The minimum, if you look down here, is 0, and it's occurring at one corner, and here at another point on the boundary. That critical point we found in the middle, 1, 1, now that we're looking at the graph, we can see that it was a saddle point, right? So we have kind of a minimum in this direction and a maximum in that direction. So that was a saddle point. That's why that didn't come into play. Even if it had been a local max or a min, that doesn't necessarily mean it would have been the absolute max or min. You still could have had something on the boundary larger or smaller. And now, the last thing I want to look at is what does this function look like restricted to the boundary. So if I just look at this boundary, the function is the parabola x squared, which is what we found. If I turn it around, look at this boundary, the function is that line, 9 minus 4y. Here, I have that parabola x squared minus 4x plus 4. And you can see why we need to check these critical values on the boundary, because there it is. It was a smaller value in between the endpoints of that line segment that makes up the boundary. So I need to check that as well, and we did. And then this last boundary was the line 2y. Okay, so there's that example. The last thing that I want to discuss are optimization problems. So in Calc 1, you did these optimization problems where maybe you had a finite amount of fencing and you wanted to close in a field of largest area. We can do that kind of thing now with functions of 2 variables. So let's say that I have a rectangular box without a lid. We want to make that box out of 12 square meters of cardboard, so I have a finite amount of cardboard that I can use. I want to maximize the volume of the box. So I want to find the length, width, and height of the box that gives me the largest volume. So I want to maximize volume, which is length times width times height. And I know that I have a finite amount of cardboard, and that's going to be the surface area of the box. And this box doesn't have a lid, so the surface area is 2 times the width times the height. That's these sides. 2 times length times height. That's these sides. And length times width, which is the bottom of the box. There is no top. I know that this surface area has to equal 12. So now, how do I finish this problem? Well, I need to solve this equation for one variable. So pick one variable, L, W, or H. It doesn't matter what you pick. Solve for that variable, plug it back in here, and now volume becomes a function of 2 variables. And you can use the techniques we've talked about in this video and the last video. That's going to be super annoying, right? You're going to get something that doesn't look so good here. It's going to be some kind of rational expression because I'm going to have to factor out, let's say I want to solve for L. I'd have to subtract 2WH, factor an L out here, and divide by 2H plus W. That's going to be annoying. Plug it back in here. I'm going to get something ugly. And then I have to find critical points and things like that. So I'm going to skip that because there's an easier way to solve this problem, and it's using a technique called Lagrange multipliers, which is the subject of the next section. So I'll see you in the next video where we talk about section 14.8, Lagrange multipliers, and we'll solve this problem.